This lecture is going to be on two very related concepts, that of basis and dimension of a vector space, or a subspace of a vector space. Okay, so and the notion of dimension is probably something that you have some intuition for. For example, we live in three-dimensional space. But the definition I'm going to give for dimension is it's going to look a little bit strange, but it's actually going to correspond to our intuition of dimension. So a two-dimensional subspace, for example, is going to be a subspace that looks like a flat plane. Okay, so the motivating question for today is, how do we describe a subspace? And you might not think there's much to that, but a subspace is typically going to have infinitely many vectors in it. And we want to say something more than, it has infinitely many vectors. Okay, we want to describe it more qualitatively. So before I introduce these concepts, let's just see an example of, why it might be useful to talk about basis and dimension. So let's start with a subspace. Okay, and I'm going to give you the subspace as the span of a set of vectors. So it's a span of, let's do 1, 1, 0, 1, 0, 1, about 2, 1, 1, and 3, 2, 1. Okay, so this is a subspace. It's a subspace because the span of any set of vectors is a subspace. It's a subspace in what dimensional space? Well, our vectors have three components, so it's a subspace in R3. And the question is, what's the most efficient way to describe this subspace? So to describe this subspace S. What do I mean by that? Well, first of all, we have four vectors in R3, right? What does that mean? Well, it means that there must be some linear dependence between these four vectors. And in fact, so note that, well, if we just take v1 and v2, those are linearly independent, actually. Right? If we have two vectors and one is not a scalar multiple of the other. So v1 and v2 are linearly independent. However, you see how I can get v3 from v1 and v2? So I should put these symbols on my vectors. Well, I'll give them names first. That's v1, v2, v3, v4. Well, it's just a sum of v1 and v2. Okay, so v3 is in the span of v1 and v2. That means that the set v1, v2, and v3 is already linearly dependent. And in fact, we can get v4 also just from v1 and v2. Do you see how we can do that? I think it's 2 times v1 plus 1 of v2. Okay, so there's some redundancy here. That's the point. And so there's actually a better way to write this subspace. So we see that we can write v3 and v4 as combinations of v1 and v2, but v1 and v2 themselves are linearly independent. So S is actually just a span of v1 and v2. Same thing. So see, I can get rid of two of the vectors in this description. Okay. And so this is where the concept of a basis comes in. Okay, so this is a set that is linearly independent, has no redundancies, and it spans this subspace S. Okay, so that's how we're going to define a basis. So a basis for a subspace S, well, it is a set of vectors in the subspace. So let's say v1 up to vm. Here we had two vectors. Such that, well, we need two things. So first of all, we need these vectors to span S. So the span of my vector is v1 all the way up to vm is S, first of all. And I need all the vectors in the set to be linearly independent. So v1 up to vm is linearly independent. Okay. How should we think about a basis? So a basis is the smallest set necessary to span the subspace. So that's one way to think of it. So it's a minimal, it's as small as possible, it's a minimal spanning set. Okay. Or you can think of it in terms of linear independence. So it's a maximal linearly independent set. We keep adding vectors until we can't add any more, or else they'll become dependent. Notice there are other ways we could have chosen a basis for the set S. This is not the only possibility. So for example, we could have chosen v1 and v3. Because these are not linearly dependent, they're linearly independent, but they still span the space S. So there's a let's look at the picture here. So for this space S, let's say I have my v1 and v2. Well, what space are these going to span in R3? Well, they're going to span a plane. So they're pointing in different directions. Okay. And you see v3 is also lying in this plane, and v4 is also lying in this plane. But they're all sort of pointing in different directions. So we could have actually taken any two of these, and that would have been a basis for this set S. So lots of examples of bases. Okay, how about, let's do a few examples. So, I mean, there's one example we've seen before, right? So E1, let's say that's that vector, and then E2 is this vector. In fact, we called these the standard basis vectors, right? We were doing linear transformations. These turned out to be really helpful. So this is a basis of all of R3. But there are many others. What would be another basis? Well, literally pick any three vectors in R3 that are linearly independent. Okay, as long as they're linearly independent, as long as one is not a linear combination of the others, then that's going to also span R3 and it will be a basis, right, by our unifying theorem. Okay. How about, let's do another example. So what is a basis for, actually let me give you an equation for a plane. So the plane, x plus y plus 2z equals 0, and in R3. And what do we mean the plane given by this equation? Well, we mean the set of solutions to this equation, right? That forms a plane. Okay. Well, what do you think? So certainly we want to choose two vectors that are on this plane. So let's just pick any two. Notice I don't want the 0 vector is on this plane, right? This plane goes through 0, 0, 0, 0, 0, I should say. But I should not include that in my basis. Why? Because a basis needs to be linearly independent. Anything containing the 0 vector is not linearly independent. So I want to avoid the 0 vector. By the way, this is a subspace. So if you were wondering about that's a good thing to wonder about, right? Because we're defining this for a subspace. But this is a subspace. Any plane going through the origin is a subspace. In fact, I think we saw this exact example in a previous lecture. Okay, well, let's just pick a random vector on this plane. So how about 1, minus 1, 0? That's a good vector on this plane. And then let's pick another one. The point is, often you don't have to be too careful about picking a basis just because there's so many. So I need to pick another vector, but I cannot pick something like 2, negative 2, 0, because that would be a scalar multiple of that one. I need to pick something linearly independent. So how about 2, 0, minus 1? Okay, 2 for x, 0 for y, minus 1 for z. That equals 0. These are linearly independent. And how many vectors do I need to span a plane? So I just need 2 vectors, okay, to span a plane. So let's take these two. So these are linearly independent, and they span the plane because they're pointing in different directions on the plane. So it's kind of like this picture. Okay, I just want to show you. Often you don't. We're going to talk about how to compute a basis in general, but often you don't have to do any intricate computations. You can just sort of reason through it. Well, should we do a weird example? So how about what is, and people actually disagree on this one. This is a bit of a controversial example. But what is a basis for the subspace only consisting of the 0 vector? So it's a subspace of one vector. Notice we have to have at least one vector in a subspace, right? Because one of the first requirement for a subspace is it must contain a 0 vector. But yeah, what is a vector of the subspace only containing a 0 vector and nothing else? So that is a subspace. And the answer, well, I can't have the 0 vector in my basis because that would not be linearly independent. So what do? Well, I just don't put anything in my set. Okay, so actually the basis for the subspace just consisting of the 0 vector is considered to be the empty set. So there's nothing in my basis. And some books actually disagree. They say, well, the 0 vector doesn't have a basis. I say that the basis of the 0 vector is the empty set, but this is something that's, if you like philosophizing about these things, and it's a fun thing to think about, should the basis be the empty set, or should it not exist? Those are different concepts, actually. But anyway, don't worry about this too much. Let's talk about why are bases important? So why are bases, I guess that's the plural of basis, B-A-S-E-S, important? There's one really key fact about a basis. We'll talk about why this is true too. So if we have a basis, then we can actually write any vector. So we can write any vector in my subspace uniquely as a combination of the basis elements. Okay, that's huge. As a linear combination. I should always say linear, right? It's a linear combination. Of the basis elements. So a basis is kind of like a coordinate system. Okay, I mean, this is literally the standard Cartesian coordinate system in R3, right? These are pointing in the x, y, and z directions. But anytime we have a basis, not just this one, but any basis, that allows us to write anything in our subspace uniquely as a linear combination of basis elements. So why is this true? Well, why? Can we write anything uniquely? Well, first of all, the basis elements span, right? Well, so we can, first of all, we can write any v in at least one way. Since the, let me give a name to the basis elements, u1, u2, up to um, let's say. So since the u1 up through um span my subset, or my subspace, right? Well, okay, great. So we can get any element as a linear combination, but why can we write it in exactly one way? Okay. So let's think about that. So what if we could write it in two different ways? Okay, so I'll find some coefficients c1 up to cm for my u vectors. Let's say I can write v like that, okay, as a linear combination of these vectors. But then let's also say I can write it as a different linear combination. So I'll put different scalars on here, okay? Still the same basis vectors, right? But yeah, let's say I have d1 to dm are my scalars. Okay, well, what if we can write v in two different ways? So yeah, if these are two linear combinations for my vector v, then we see what we can do. We can take these two and subtract them. So I'm going to do this one minus that one. Well, both these are equal to v, so that should be v minus v, which is 0. Right, so I'm going to do c1 u1 minus d1 u1. So I'll just collect the coefficients like this. So I'm subtracting both sides all the way up to cm minus dm times um. And again, yeah, what is this going to equal? It's going to equal v minus v, which is 0. Okay. But what do I have here? I have some combination of the u1 up to um equaling 0. Let's use the fact that these are basis elements. So not only do they span, they're linearly independent. Right? So what does that mean? If the u, so yeah, let's just say, but all of these vectors u1 up to um are linearly independent. What does that mean? Well, it means that all of these coefficients are 0, right? Because the linear independence, by definition, says that the only way I can write the 0 vector as a linear combination is if all the scalars are 0. Okay, so c1 minus d1 has to be 0, which means c1 is d1. c2 minus d2 has to be 0, which means c2 equals d2, all the way up to a cm equals dm. So what did we just prove? Well, we proved that these were both the exact same linear combination to start with. Okay, so if we assume we can write it as two different linear combinations, well, oops, turns out they're both the same linear combination. So there's actually only one way to write every vector as a linear combination of the basis elements. Okay. One more important fact about a basis is that, so here's another fact. I won't prove this fact because it's not supposed to be a proofs class really, but it'd be good to think through this on your own. You know, why is this true, what I'm about to write? So yeah, if S is a subspace again, if S is a subspace, then here's the fact. Any basis for S, remember we can have many different bases. So any basis for S, it's actually going to have the same number of vectors in it. And that should make sense intuitively, but it's a little bit tricky to prove. But any basis should have the same number of vectors. Okay. For example, for R3, I mean, it's easy to see for R3, right? Because, well, Well, I mean, it's not too hard to see in general, but yeah, what if we have a basis for R3? Well, it spans R3, so it has at least 3 vectors, but it's also linearly independent in R3, so it has at most 3 vectors. So it has to have exactly 3 vectors. But we're saying this is true for any subspace, right? Not just the vector space Rn itself. So any basis for a subspace has the same number of vectors. That allows us to define the concept of dimension. So the dimension, very important definition, the dimension of a subspace is denoted dim S, like this, is, dimension, is the number of vectors in a basis. In any basis. By the above fact, it doesn't matter what basis we choose, it's going to have the same number of vectors. So we just have to find one basis, the number of vectors in that basis, we call the dimension of the subspace. Okay. Example. This subspace, S, that we started with, is 2-dimensional. Okay, we were able to write it as just a span of these 2 vectors, and these form a basis. So these 4 vectors actually are just spanning a 2-dimensional plane in R3. Okay. Great. So I think it's maybe time to talk about how do we actually compute a basis in general? Because we just did an example where you could kind of see what the basis had to be just by looking at it. Well, what if we had a more complicated situation? So how do we actually compute a basis for a subspace? Similarly, how do we find a dimension of a subspace? Well, the way we find a dimension of a subspace is, well, if we find a basis, we're done, right? Because we just count the number of vectors in that basis, and that's the dimension. So like I said, 2 very related concepts. Once we find a basis, we also know the dimension. I'm going to give you 2 methods for computing a basis. So there are 2 methods. The first method is called the, well, actually it doesn't really have a name, but I'm going to call it the column method. And then the second method, I'm going to call it the row method. They're both going to deal with matrices in echelon form, so things we're already familiar with. Let's make this into a little table, actually. Okay, so how does this work? We're going to do some examples of this, too. Okay. So, well, what's the typical setup? Okay, so actually, yeah, let's put that over here. So, given some space S, some subspace, which is a span of some set of vectors. This is a very common way to describe a subspace. What is a basis for S? That's the question. Well, you might say, well, wait a second. If S is a span of these vectors, isn't V1 up through Vm already a basis? Well, the thing is, these might not be linearly independent. Okay, so these are not necessarily independent. Okay. So how do we compute a basis? Well, the most natural idea is to form a matrix with my vectors as columns, as we've done many times. So form a matrix A. And what is this matrix A going to look like? Well, I'm just going to put my vectors as columns. Okay, so I'll just indicate that like this. And then step 2, we're going to reduce A to echelon form. row echelon form. You don't have to go all the way to reduced row echelon form. Okay, then what are we going to do? We're going to look to see where the pivot columns are, which columns have the pivots. And then we're going to select the original vectors v1 up through vm that correspond to pivot columns. Okay, so reduce to row echelon form, and then I want to keep the original vectors v1 up to vm that correspond to pivot columns. Well, why does this work? I won't go into a ton of detail here. I just want to give you some idea. It's unsatisfying, right, for me to just tell you how it's done without explaining the reasoning behind it. So yeah, why does this process work? Well, it's because when we go down into row echelon form, when we do row operations to this matrix, that actually preserves linear relations between the columns. Okay, so if we start with linearly independent vectors, they're going to stay linearly independent. If we have linearly dependent vectors, they'll stay linearly dependent. And any kind of relation, for example, 2v1 plus v2 equals 4v3, that will stay, right? Even as we do row operations, we'll still have 2 times the first column plus 1 times the second column will equal 4 times the third column. So relations like that will persist. So let me just write that in a few words. So linear relations between the columns are preserved by the row operations, elementary row operations. And so the idea is that when we get down to row echelon form, we're going to just easily be able to see which rows we can sort of, or which columns we can throw out in order to get a linearly independent set, for example. Okay, well, how's the second method work? Let me tell you both methods maybe first, and then we'll do an example. So in this in this example, we're actually going to sort of flip the matrix. So that's why I call it the row method. So we're going to form actually A transpose. It's our first time using the transpose. So what is A transpose going to look like? Well, I'm going to turn my column vectors into row vectors. So I'll put my first vector, I'll flip it this way and then put it as a first row. And then I'll go down the rows. Okay. And now again, I'm going to reduce this to echelon form. I'm going to reduce A transpose to echelon form. Then, so here's the cool thing about this method. Then the non-zero rows meaning pivot rows, basically, right? Of this new matrix, the echelon form matrix, themselves form a basis. For S. Okay? So I look at the row echelon form, and then the non-zero rows of that row echelon form, I can just take those vectors themselves. Okay, I don't want to say, oh, which original vectors do these correspond to? That actually won't work. So it's a little tricky. I mean, yeah, again, we'll see both of these as an example, but I want to give some idea, why does this work? Why can't we just take the new rows that we get? Well, it's because the span of the rows and yeah, it's preserved by the row operations. That takes some work to show, but For example, if I take row 2 and subtract 2 copies of row 1 from it, I'm actually not changing the span. So yes, row 2 will change from that process, but my new row 1 and row 2 will span the same space as the original row 1 and row 2. Okay, so again, a couple of warnings. So yeah, let me write a little bit more. So here's our warning. Put this in red maybe. For this first method, do not take the columns from the echelon form matrix. Okay, why? Because those columns that I get when reducing this to echelon form, those might not even be in my subspace anymore. Okay, so it's not like this. So when I do row operations, I am changing the space spanned by the columns. Okay, so I have to, all I'm doing when I go down to row echelon form, I look at where my pivots are and I take the original columns. Okay, and with this one, there's also sort of a downside. The basis I get from using this second method, so the basis, it might not include any of the original set. So it might just be completely new. Because again, in this case, I am taking the rows I get once I get down to echelon form. The non-zero rows, at least. So yeah, this might include vectors not in the original set. Okay, well, that's enough words, probably, but yeah, I did want to outline these two methods. Let's see both of them in action. So let's do a pretty big example, actually. So we'll do 4 vectors in R5. So find a basis for the space S, some subspace of R5, spanned by the following 5 vectors. So let's do, all right, 1, -4, 0, 7, 3. I have to be very careful not to mistakenly copy down one of these numbers because that could change the solution completely. -2, 8, 0, -14, -6. That's my second vector. 5, 8, 1, -2, 0. That's my third vector. My fourth vector will be -3, -16, -1, 16, and 6. Okay. Should we give these names V1, V2, V3, V4? All right. What method should we use? Let's use the column method first. So here's method 1. I formed the matrix A where the columns of A are my vectors. So we have 1, -4, 0, 7, 3, and then we have -2, 8, 0, -14, -6, 5, 8, 1, -2, 0, -3, -16, -1, 16, 6. Okay, now we have to go to echelon form. And you might be asking, wow, is he really going to do all the row operations? Well, yes and no. So I already did them ahead of time. So I'm just going to tell you. So this is a bunch of row operations. I even went down to reduced row echelon form. So this is what you get when you do that. 1, 0, 0, 0, 0, -2, 0, 0, 0, 0, 0, 1, 0, 0, 0, and then 2, -1, 0, 0, 0. This is reduced row echelon form. Here are 2 pivots. Notice that above the pivots we only have zeros, and both the pivots are 1, so that's what makes it reduced. You don't have to go down to reduced row echelon form. What's the point? The point is we have pivots in columns 1 and 3. Right? So the pivots are in columns 1 and 3. What does that mean? It means we should choose V1 and V3 as our basis. So this set right here, this is a basis for my subspace. Okay, so I didn't need all 4 of these. It turns out I only needed 2 of them. What is the dimension of my subspace S? Well, it's 2. Right? So that tells us that actually these 4 vectors, very similar to this picture, it span a 2-dimensional plane in R5 this time, in 5-dimensional space. Okay. Notice, okay, be very careful. So I'm not saying take this vector and the third one. So note, this is this is the warning again. This vector is not in S. Okay, so don't take the vectors of the echelon form. Take the vectors in the original set that correspond to the pivot columns. Okay. Okay, let's look at method 2 really quick. All right. So again, I did most of the work ahead of time, but let me say what matrix we're going to look like. We're going to look at the transpose this time. So 1 minus 4, 0, 7, 3, minus 2, 8. Remember what the transpose is? You just the columns become rows and vice versa. Minus 6, 5, 8, 1, minus 2, 0. Finally, minus 3, minus 16, minus 1, 16, 6. Okay. Now, I need to get this down to row echelon form. It's going to look completely different than this one. See, in both cases, I'm using row operations. Okay. I'll tell you what I get. So I did not go all the way down to reduced row echelon form this time, just to show you that we don't need to do that. And because I noticed the numbers are going to get a little bit nasty. So I have a 28 there. 1, minus 37, minus 15. And then we get 2 rows of all zeros. So again, we get 2 pivots. That's not an accident. We got 2 pivots up there. Okay, what is this telling me? Okay, well let's recall what we're doing. So we want to take the non-zero rows of the new matrix. So we want to take the non-zero rows of this matrix. So what is my basis? Notice that first one just happens to be, this first row happens to be V1, right? That didn't change at all. But my second row is completely new. That's not one of my original vectors. I'm going to take both these rows and minus 15. So this set is a basis for S. Okay? I can't really see what that is. Let me just redo these last 2. So that was a minus 37, there's a comma here, and a minus 15. Okay, so this is another basis for S. We could have taken either of these, and these would both be correct. Okay. However, we had to be careful, right? So you don't want to get these methods confused with one another. We could not have taken the first 2 rows of the original matrix. That's because these row operations actually, like some of them swap rows, right? And notice the second row is actually just a multiple of the first one. So we definitely would not want to take these first 2 rows. In this second method, the row method, I really do need to take the rows I get from the echelon form. Okay, so this is a basis. But taking the first 2 rows of this one would not be a basis. Okay. Let's go to a new page. So here's another kind of question. So what do we see so far? We have a bunch of vectors. We want to reduce it down to a basis. Can we do the opposite? So can we expand the set? Let me give you two vectors in R3. 1, minus 2, 2, and 0, 1, minus 1. Can we expand this to a basis of all of R3? In other words, add as many more vectors as we need to in order to get a basis. So first of all, note, these are linearly independent. I mean, this one kind of looks like a multiple of that one, but it's not because of the top entry. So these are linearly independent. That's good, because if they weren't, then we would not be able to expand that to a basis. We would have to get rid of one of them and then expand it to a basis, right? Okay, so how do we do this kind of problem in general? So here's the idea. We want to make the given vectors. It's helpful to actually, you should try to think through this problem on your own. How would you expand these two into a basis? Yeah, I'm going to say one way you can do it. So make the given vectors the first two columns in a matrix. Okay, so I'm going to start out with these two. We're going to use some ideas that we just saw. So I'm going to make those my first two columns. And then I'm going to fill up the remaining columns. With, so what's the danger? We need to make sure we're picking things that actually span all of R3, right? So we want to pick enough vectors so that we know we span all of R3. Then we can use the previous idea to kind of whittle them down. And again, we want to make sure that these two stick around. So fill up the remaining columns with any known basis of the subspace. I mean, in this case, it's R3. So what's the basis for R3? 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. Then, well, we just do what we did before. So let's do the row operations. I'm going to use I'm using the column method from before. So I'll just say that really quick. So then use the column method. That we just learned. Okay, we'll keep the first row as is. We will take the second row and add 2 copies of the first row. So we get this. We'll take the third row and subtract 2 copies of the first row. So we get this, minus 2, 0, 1. Okay, and then we're going to keep the first 2 rows as is. Then we'll take the third row and just add a copy of the second row. So this is 0, 0, this becomes a 1, and this stays a 1. Great, okay. We have pivot there, and a pivot there. What does that tell us? So we have pivots in columns 1, 2, and 4. Do we take these 3 vectors? No, we go back to this matrix, the one we started with. And we take these vectors. Column 1, column 2, and column 4. Okay? So the answer, one possible answer, is so we have these 2 vectors, right? They're the ones we started with. That's what we wanted. We wanted to expand a set. We didn't want to get rid of these. That's why we use that column method. And then we also have to apparently add this one. We could not have added 1, 0, 0 actually, because you see that it's actually what this is saying is that this third column is a linear combination of the first two. There's no pivot here. Okay, so this is one possible answer. Okay. We could add 0, 1, 0. There are many other vectors we could have added, but we just need one, and this is guaranteed to give us one. Why did we have to make our two vectors the first two columns in the matrix? Well, what if we made these three the first three columns? Then you see what we get was we'll just get the three pivots there, 1, 1, 1. And it'll tell us to take these three vectors, which is great. I mean, that is a basis of R3, but it does not include the first two. So that's why we stuck our first two in there as the first two columns, because we wanted the pivots to occur there. We definitely wanted pivots there. And then we wanted to see, well, where can we get a third pivot? Okay. We put all three vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1 in, just for good measure. And it turned out we only needed this one. But again, we put them all in just for good measure because we do want to make sure that we're going to span R3. And then we use this column method. We can find which ones to get rid of, essentially. Okay. Should we do one more example? Let's do a null space calculation. So let's find a basis. Here's another example. Find a basis for the null space of a matrix. It comes up very often in practice where you want to compute a null space of a matrix. And often it has a very direct physical meaning, the null space of a matrix. We'll talk about that a little bit later. So find a basis for a null space of A where we'll have to tell you what A is. Should we just make A the same matrix we had before? Oh, I don't want to copy this thing down again, but I guess I'll copy it down once. So A is this matrix. Okay. And what do we mean again by null space? Well, yeah, let's recall that. So what is a null space of a matrix? It's the set of all solutions. To which equation? The equation AX equals 0. Okay. By the way, what's my vector X going to look like? It's going to be x1, x2, x3, x4, right? It's going to have 4 elements. So I need to find all the set of solutions, x1, x2, x3, x4, to AX equals 0. Okay, how do I do that? Well, I make the augmented matrix, this, and then a row of zeros. I'm not going to write down this matrix again. But let's say, after all the row operations, what do we get? I think I already wrote that down. It's 1, minus 2, 0, 2. And then the second row is 0, 0, 1, minus 1. And then we get a bunch of 0 rows. And then I guess I have a... well, what's on the other side of this red line? Just a bunch of zeros, right? Okay. So again, I need finding a null space is nothing new, right? It's just solving a system of equations. It's solving this system of equations. This equals 0, a 0 vector. The thing that is new is we have to describe this efficiently. Okay, we have to find a basis. And let's find a dimension also. That will be very easy once we find a basis. Okay, well, what is this matrix saying? So, well, first of all, I have 2 pivots. I have two free variables also. What are my free variables? x2 and x4. They're free variables. We can just sort of write down the solution, right? So x1, x2, x3, x4 that's the nice thing about this reduced echelon form. We can just sort of write down the solution. Why am I saying that? Well, because what is this second row telling us? It's saying x3 minus x4 is 0. In other words, x3 equals x4. So let's set x4 equal to, it's free. We can set it equal to some parameter t. Well, x3 is also t. X2, what is, x2 is also free, so let's call that s. And then x1, what is the first row telling me? x1 equals 2x2 minus 2x4. That's what the first row is telling me. So it's 2s minus 2t. Okay. Can we write this in vector form? So what do I mean by that? I just mean this. So we have s and we have t are our two parameters. I'm going to turn those into scalars. I think we might have done this before. So I'm going to write it as s times, and then here I have a 2, a 1, a 0, and a 0. Those are my s, right, coefficients. And I'm going to write this as t times, what should I write in this vector? Minus 2, 0, 1, 1. Okay. Oh, well, this is beautiful, though, because look at what I just wrote down. My solution set is any number s times that vector plus any number t times that vector. So in other words, the null space is the span of this vector and this vector. By definition of span, because what does span mean? It means take all linear combinations. That's what I'm doing. I'm allowing s and t to be any numbers. And so my null space is the span of these two vectors. Is this a basis? So we know it spans, right? Are these linearly independent? Yes, because they're two vectors. When we have two vectors, we can check linear independence just by looking if one is a scalar multiple of the other. So these span the null space, and these are linearly independent. So, so this is a basis. These two vectors form a basis. Okay. And also, what did we just find out? We found out that the dimension of the null space is, again, 2. So it's two-dimensional. There are two vectors and a basis for the null space. Okay, we're running out of time. Let me leave you with the problem, actually. So, problem. What if I want a basis for the null space of A? Same matrix. But I want a basis, I want to specify, there are lots of bases. We just found one. What if I want a basis that includes the vector? I insist that my basis includes this vector. I like this vector. I want this to be in my basis. Okay. Well, how do I do that? Well, can I just add that to my set here? No. You can't just add it to this set, because then I would have three vectors. Right? Those would, we just established that 2 vectors is the maximal linearly independent set. Right? If we have any more vectors, we will be linearly dependent. Okay? That's what it means to be a basis. It spans and is linearly independent. So I can't just add this to my set, but I do what I did before. So let me get you started, actually. So what do? I definitely want this vector, so I'll put that as my first column in the matrix. Okay? And then I know that these two vectors are a basis for the null space of A. So I'm going to put those as my second and third columns. Okay, then what do? I row reduce the matrix, Gaussian elimination. And Well, actually, what am I going to get? You can almost see what we're going to get because these first two columns are not linearly, they are linearly independent, right? One is not a scalar multiple of the other. So I should get pivots in both of these columns. So I should have a 1 there, and I should have a bunch of zeros here. Okay, now I don't really care what I get in the third column. But you see these two ones here, this one and that one, they're telling me I need to take the first two columns. Okay. So this is another basis. For a null space of A, and it includes the vector that we wanted, right? So yes, the answer is you do add this vector to the set, but you must keep in mind that you introduced some linear dependence, and so then you have to use this column method again to identify which columns to keep, and those will correspond to the pivot columns. And this, we actually don't get another pivot. By the way, there's one thing I should have asked before I even wrote down this matrix, and that is, is this vector v in the null space to begin with? It had better be in the null space if it's going to be part of a basis, right? So how do we check if something is in the null space of a matrix? Well, it has to satisfy this equation, right? So what is that saying? If I put this in for x1, x2, x3, x4, I multiply by this matrix, I get 0. So in other words, there should be a 0 vector, right, by the way. It's saying if I take 0 of the first column, plus 1 of the second column, plus 1 of the third column, plus 1 of the fourth column, I get 0. And notice I do, that's true, right? If you add this column, and that column, you get 0 in every entry. So that's pretty cool. So you should think about vectors in the null space as giving you linear relations between the columns that they satisfy. Okay. So for example, what is this first one telling me? The fact that 2, 1, 0, 0 is in the null space? It's telling me that 2 times the first column plus 1 times the second column is 0. Okay. Or in other words, the first column is negative 2 times the second column. Or the other way around. The second column is negative 2 times the first column, which is true, right? We see that actually this is just, the first column multiplied by negative 2. So that's just kind of a preview of, how we're going to use the null space. But elements in a null space tell us linear relations between the columns of our matrix. Okay, thanks for watching.